So, welcome back to the course on architectural design of ICs. So, in the last class we have seen the codic architecture. So, today we will discuss about actually few other topics are left, which is again we will see that how one FFT, or that means a bigger circuit, which is any transform circuit like FFT, IFFT, DST and then DCT, some kind of transforms or some kind of system approach, if we could take as an example at that time, how we can design that we will see. Apart from that, whenever we are talking about this architectural design, mostly we are in the digital design side, right. So, at that time we have seen several architecture, we have seen that means optimization, all these things we have seen. But what we have not considered till now, that is the timing issues or the issues which are related in mostly in the digital design part. So, that we have not seen till now. Okay. So, today we will see these issues in timing closure, what are the issues are available, or what are the factors which basically degrades the performance of the, though that means why I am telling that, or why you need to that means know about this factor, because whatever optimization you have done, right, but still if you are whenever you are making your chip, at that time it should be perfectly in the working condition. That means whenever you are, that means after the chip got fabricated, your chip should be work properly. Okay. So, whenever during the testing phase, it should be tested okay. So, that is why it is not that for any other issues. So, you have made this optimization for area, power, speed, all the things we have made. But if your chip is not working because of some other factors, then whatever optimization you have done for your designing your system, that is not at all meaning anything. Okay. So, that is why whenever you are designing, at that time some of the issues also you have to be keep your mind. So, today we will discuss actually not in details, I can describe, because itself this timing closure itself, it takes so much of time or so much of, that means effort to learn this particular procedure, but I can give you some of the overview or some of the basics what you have to know. But if you want to learn, or if you want to know more, then you have to search in the, that means internet, for the latest upgradation in this particular direction, or if you are interested, then also please you also can let me know that okay, I am interested, then please I will help, that means try to help you whatever is my limit. Okay. So, today we will start, or we will see the issues which are related to digital design. Okay. So, in digital synchronous circuit, actually in digital design, there you might find two type of circuit. One is this synchronous circuit, another one is asynchronous circuit. Why I am telling? Actually, apart from that, actually that is not the case. In digital design, it is the starting that there are two type of circuit. One is this combinatorial circuit, another one is sequential circuit. In sequential circuit, you might find two type of circuit, that is one is synchronous circuit, another one is asynchronous circuit. Okay. So, what is synchronous circuit? Synchronous circuit means in the system there will be one single clock. Okay. That means all the, that means the corresponding sequential elements which are present on that particular design, both will be clocked by the same clock. Okay. So, that means depending on the same clock, all the, that means sequential element, they will change their state. It is not that, but in case of asynchronous, there you might find more than one clock. That means one clock that may be run at f1 megahertz or f1 hertz or f1 gigahertz, and another clock in different frequency which may be f2, okay, or it may be more than that. So, that means there is the operation of the sequential element, that is not synchronous in case of asynchronous circuit design. So, when actually both has some of the advantage. Okay. So, where to use synchronous design, where to use asynchronous design, again itself it is a that means technical knowledge, you know. Okay. So, but I will give a brief idea where you can use this synchronous design and where you can use asynchronous design. So, whenever we are doing this timing analysis means why I require to do this timing analysis, because to meet the that means whatever to find out this f clock. So, in this particular system you see this f clock is the clock basically which is connected to each of the synchronous element which is present within this digital synchronous design, right. So, what will be the maximum achievable clock frequency for this particular design? So, that you only able to know by doing this timing analysis. So, that means suppose if you see that this, if you just have noticed that suppose one that whenever we are talking about the processor, let us say Intel Pentium 4, that may be run at let us say 2.8 gigahertz. So, 2.8 gigahertz is the clock frequency where that processor can run. So, why it is needed? Because depending on that clock frequency, now higher the clock frequency, that means the corresponding computation time which is related to this your instruction fetching or your instruction to be executed on the CPU or in the processor, that becomes lesser. Okay. So, that means you can do the processing or you can do the computation in the processor in a faster way if the clock frequency is on the higher side. Okay. So, that is why our mostly or our that means primary intention always is to maximize this clock frequency. Okay. And whenever we have to calculate this clock frequency, we have to do this timing analysis. How you can do? Timing analysis can be done in two ways. One is static timing analysis, another one is dynamic timing analysis. Okay. So, what is static timing analysis? Static timing analysis is, it uses these analysis techniques on the net list to define this f clock max. Okay. But in the dynamic, that means here whatever is the corresponding critical path means from the input to the output, which path it is taking the maximum time, that is the critical path for your system. So, that particular path, how much time it is taking, so 1 by that time is basically your frequency or the maximum achievable frequency. Then you can ask that if that is, that means if I make it lesser, that means if the time period, suppose the that critical path requires the time of let us say 10 nanosecond, but if I make that clock frequency of 9 nanosecond period, so at that time what will happen? So, at that time what will happen? Before the execution of that path, your data will be changed at the input side, though your operation is still not, that means that is yet to be completed, because it is required 10 nanosecond, but at the input what you are doing? You are changing the input at 9 nanosecond or before that 10 nanosecond. So, at that time what will happen? Though the operation is still yet, that means that is not completed, but you are changing the data means it will take the next data for the computation again. Okay. So, that means at the output you will not get the proper result. So, that is why this is actually, that is not all for all the things, it is not the case that the critical path basically corresponds to the this considering the gate delays only, okay, gate delays and net delays. So, if we consider this gate delays and net delays for that particular path, so it is not that only because of those factors the critical path is 10 nanosecond, it may be more than 10 nanosecond. Okay. So, why there is this more than that 10 nanosecond, that we will see. Okay. But in dynamic timing approach, this dynamic timing analysis approach, what we do? We use this simulation based timing analysis. Simulation timing analysis means we give some of the, that means selected input stimuli, means some of the, that means what I said, that for static timing analysis the input is not defined, that means the combination of what will be the corresponding combination of input, that we have not considered. This is here we do the rough estimation based on this the available information from the gate delays and the net delays, which is dependent on the totally on the library. That means from the library I will get those information, and based on that I can calculate this what will be the timing requirement for that. But in dynamic timing analysis, what we do? We basically gives a selected set of stimuli, selected set of inputs or the combination of inputs to check what will be for that particular or for those particular combination, what will be the timing requirement for this particular circuit. Okay. So, that means what and why I need this dynamic timing analysis, because in during the testing, how we can do the testing? During the testing phase, what we will do? We will give some of the test vector to the circuit for properly whether that is properly working or not. So, during that time, whenever we are that means giving the proper, that means in the real time whenever we are giving the inputs, so at that time your circuit may fail. So, that is why from the beginning if we check by that means providing some of the input combination to the design, and then if we do the timing analysis. So, at that time the probability of that failure that becomes reduced, or my intention is to reduce those, that means the probability of that failure. Okay. So, that is why we do timing, this dynamic timing analysis. So, this is the two condition where we use static timing analysis and where we use dynamic timing analysis, but for the particular, that means for any system design which is has to be like in the, that means chip format, or if it is has to be run on the real time. So, at that time both the timing analysis we have to do, whether that is static timing analysis and that is the timing analysis. Okay. So, here you see this static timing analysis seems ideal since it is done by a design tool that starts from the netlist and run automatically. Okay. Means what I said, that based on the library information about the gate delays and the net delays, the tool itself it calculates the corresponding timing requirement for that the critical path or for that the system design. However, the static timing analysis may report pessimistic results and report delays that will never occur during operation. Okay. So, that means here whatever results we will get that is one rough estimation of the, that means this circuit, that means the delays information. Okay. So, that is why this report may be, that is why it is says that the report may be pessimistic results. But in case of dynamic timing analysis, this is, that means dynamic timing analysis, what do we do, when we do or why we do, basically to check what will be the timing requirement whenever we will test it in the real time environment. So, that is why this dynamic timing analysis is very much important, because we can combine it with the simulation which we do for the functional verification. Not only for the functional verification, during the testing whatever test vector we will give, so those stimuli we can put now, that means at the simulation itself now we can put, and then we can check the timing analysis or the timing requirement for that particular design. However, this dynamic timing analysis may be too optimistic, and in particular if we do not simulate the worst possible case. So, that means here when this will be, that means too much optimistic, because it is not the case that all the time we can provide all the test vectors and we do dynamic timing analysis. Why? Because if the size of the test vectors, suppose for a 64-bit adder design. Okay. So, for a 64-bit adder design, so what will be the number of test vectors? That is 2 to the power 64. So, 2 to the power 64 number of test vectors, application of that, generation and then application and then do the simulation, it will take too much of time as well as too much of effort. So, on that particular case, actually those who are working on the testing area, so they at that time see that what will be the optimized test vector to produce or to, that means testify the circuit whether that is working properly or not. That means, based on the reduced set of or optimization is done on the test vector itself, so that the number of test vectors becomes lesser, but still I can check all, that means the possible functionality working or the proper functionality of the design. Okay. So, what will be that number? What will be that optimum number? Those who are working on the testing area, so they basically work on that. What will be the minimum number of test vectors and what will be the combination of test vectors? Okay. So, and then for that your my system will not failure. So, those type of things do who that means who the people working on the testing and verification area. Okay. But these two particular case we use for any VLSI chip design. Okay. So, this static timing analysis, what is the idea of static timing analysis? Suppose I am having the input to the output, whatever systems, that is the block diagram representation of the that system we have seen in the earlier slide. Okay. Now, consider one particular, that inside of that system design. Okay. So, inside of this system, if there are these two are the register or the sequential elements, and they are being connected inside between this combinational logic, 3 combinational logic. This is C1, this is C2, this is C3. So, then this is the application of input. So, this is a delay from input to the register, which is happening because of this combinational logic. Then this delay from register to register, and considering the corresponding factors or the corresponding logic which is available in combinatorial logic, and delays from register to the output, which is again passing through another combinatorial logic. Actually, why these 3 are different and when these 3 will be merged? If these registers are not there, at that time this total delay will be this C1, the delay of this C1, delay of C2 plus delay of C3. But as I have put this registers in between, that means what? I am, this data dependency has become now clock dependent. Clock dependence means though there is a change, actually in combinatorial circuit what happens? If I change any of the input, the output automatically tries to change, or the corresponding logic elements, they starts their operation. But in sequential element, unless and until you are finding the edge of the, that means whatever logic, whether if it is edge triggered. So, unless and until it is finding the edge, it will not start its operation. So, that means now what? It is dependent on the clock, it is not dependent on the data. But in combinatorial circuit, if you change any signal, so automatically that will reflect at the output. But in sequential element, if you find the edge, then it will go for checking the what is the value present at the data. So, based on that data, now the output will change. So, that is why now this is which is getting highest priority, the clock one. So, that is why this is clock dependent, not data dependent, sequential element. Okay, got it. And that is basically for that particular property, if we put the resistors in between, so that becomes this, at that time this C1, C2, C3, that became individual to each other. Okay. So, now we have to calculate the timing analysis for this. Okay. So, this STA, how we can calculate? So, that means whenever there is, so there are input to the registers, then register to the register, then register to the output. Okay. So, here you see inside of this register to register, whatever is the logic, so that will be considered as the timing requirement, minimum timing requirement for the corresponding clock. So, then what will be the corresponding value for this? The value for this will be T clock to Q. T clock to Q means what is the meaning of this? This is the delay of the flip flop itself. The delay of the flip flop itself means from clocking to the delay, that means the output, which is the Q. It has actually, if you just remember the that corresponding, that means internal structure of flip flops. So, 4 NAND gates are there, right. So, that means it has to, the clock has to pass through 2 levels of this this AND gate, sorry, NAND gate. So, that means it also has some of the flip flop itself has some of the delay for propagating this clock to the output. Okay. So, that delay is basically mentioned over here. This is T clock to Q. Then whatever is the this logic delay or the corresponding gate delay for this combinational circuit, that will be again considered, or that again it will come to this part. Then this routing means this is nothing but the delay which is associated for the, that means net delay. Net delay means as they are being connected from gate 1 to gate 2 or gate 2 to gate 3, as the wire is connected. So, because of the wire, it also, as for the wire there is this RC component. So, because of that it also takes some time to signal, that means for the signal to traverse from one point to the another point or one node to the another node through that particular wire. So, those delay will also be considered in this case. So, that is this T routing. And then again there is another, that means delay which is also associated for this computation of this minimum clock period, which is this T setup. So, what is setup? What is setup time and what is hold time? I think that is basically mentioned, or that can be recalled in the, or that is mentioned whenever in the basic digital design. But still we will discuss what is the setup time and hold time. We will revisit that. Okay. But this T setup, that is one of the requirement for this particular flip flop. Why that is required? Okay. So, that we will see later of this presentation. Okay. So, after that, that means all these particular things will come whenever we are computing this T clock minimum. But then again, if the clock has some of the skew, so if the clock has some of the skew means what? What is the meaning of clock skew? In synchronous design, you might have to be very much cautious, because as this clock is synchronous to each of the, that means sequential element. So, at that time so many factors are basically associated with that. One of them is this clock skew. Then not only clock skew, clock jitter is also there. So, what is clock skew, what is jitter, that we will discuss that during, that means in the other slides. But here actually for the time being, if you consider, if this clock T clock, that means this, if this clock has a skew, then, and that is in favor means if from this path to this path, this clock skew is basically positive. So, at that time this T skew will be minus from the corresponding delay. Why? Because here skew works in the favor of us. That means favor of us means favor of the circuit, now it works. So, if in favor of circuit it works, as this direction, the clock direction is basically traversing from this side to this side. So, that is why this clock Q, that means the data is also flowing in this direction and the clock is also flowing in this direction. So, at that time it is in favor of us. But if the clock is basically supplied on the opposite side of the data, suppose in this direction data is supplied, but in the opposite direction if the clock is supplied, so at that time this Q will not be in favor of us, that will be against of us, or the against of us means against of the design. So, at that time this Q also will be added for finding out this T clock minimum. So, why actually what I said in the beginning, that these things or this static timing analysis that has been done through the EDA tool automatically, right. So, that means whenever this, depending on this kind of factors, the EDA tool itself automatically computes what will be the corresponding values of T clock minimum considering each of these factors. Now, each of these factors how we will get this T clock to Q, the delay for this flip flop, that we will get from the library. How many levels or what are the, that means gates are connected for this logic delay. So, that again you can compute from the library, or you can get the information from the library itself. Then what will be the net delay, again that will be again come from the library itself. What is the setup requirement of the flip flops, again that comes from the library. And then what is this clock skew, then again that is also you can get from the information provided to you only. So, that means all this information is already stored in the library. So, the tool itself it fetch those data and it computes based on this equation, and it shows to you that okay, this is the minimum clock period requirement for your design. Okay. So, here you see that STA takes delay on the clock connection into account, which is called as this clock skew. The effect of clock skew is highly dependent on the circuit topology. That means, how you have, what topology you have used for the circuit representation, that is an important factor over here for this Q. So, if you just see that if I make this, that means if I supply this clock in the opposite direction of the data, so at that time clock skew will be added to this, that means this corresponding equation. Okay. So, here you see skew works against us. Okay. So, the effect actually the effect of clock skew is highly dependent on circuit topology, that we have already seen, but the physical layout of the chip including the placement of the components and the routing of the wires. That means, routing of the wires means how this clock is, that means in which direction I am supplying the clock, that is dependent for computing this Q. So, if it is against the data, that means opposite to the data, then it will be added. If it is same direction with the data, so at that time it will be subtracted. Okay. And the best clock skew is 0. Chips will distribute the clock signal so that it arrives at every flip flops at exactly the same moment. Suppose in a chip 1000 sequential elements are placed and you have only one clock source, that means that clock will be connected to one pin. So, from that pin now you are supplying to 100, let us say, sequential element. From that particular point to reach the maximum, or that means the farthest sequential element present from that particular pin. So, it will take the maximum net delay or the maximum delay for traversing that clock to that particular element. So, that means at that time skew will be high enough for that, or those, that means that particular path. Okay. But what I said, skew is sometimes it is better, sometimes it is, that means not, it is worst case condition for our circuit design. Okay. So, but in ideal case, if we consider this clock skew is 0, that means clock skew is 0 means each of the sequential element has been connected to the clock in a uniformly distributed network. That means suppose from clock connected to the 1 and clock connected to the farthest element, they takes the same amount of time. If they take the same amount of time, at that time this clock skew we can consider that as a 0. So, clock skew means is the time gap between the closest one to the furthest one. So, this is the, that means this concept of this timing analysis, static timing analysis, okay. And this clock skew is an important factor, not only clock skew, then setup time and then this clock to queue, then this T logic. So, during optimization what we actually till now what we have done, this combinatorial design or the combinatorial logic part, we have done reduction of the timing or reduction of the area on those particular path, but we have not considered the other things which are associated in the whole timing closure calculation. So, that we will be seeing continuation of this particular lectures. Okay. So, thank you for today's class. Again we will meet on the next class.